Hey guys, I just want to do a quick overview of how I've been progressing with the robot motor tuning, and just give you a little bit of a view of what I got cooking over here. This is my remote desktop screen. So this is actually of the this is actually the desktop in the office, and this is how I see it. Here's the robot on the webcam, which is sweet. Got a couple of terminals that are open on the desktop and some in the robot itself. And then here's a Python script that's running inside of the desktop, helping me tune some of these motor parameters. So just really quickly, we have DC motors, right, which you just power on and off in either direction, but it's like direct current. And we have encoders hooked up, and so we just want to make sure the motor hits a desired encoder count. And we're using a PID controller to do this, which is should be a fairly straightforward process. Basically, it's just looking at, that you're mitigating your error. So when you send us a new coordinate for the robot, it looks at its current position, and then compares it to where it's supposed to be, and says, okay, this is my error, and all the control algorithms are based off of that error. So PID will have a proportional term, an integral term, and a derivative term. So the proportion of error, derivative error, and an integral of it. And this is really useful because it's a very predictable behavior. So the proportion just looks at, okay, what set point am I supposed to be at? Where am I now? Okay, if that's a big value, make a big change to the motor speed. The derivative of the error, would look at, well, okay, I'm closing out the error quickly, so maybe, let's slow it down a little bit. And then the integral term is great for if you have a small error that's accumulated over time, it's going to nudge it the rest of the way. So what I've done here is, if I run the right program, is wrote some algorithms to help me sweep through different PID parameters, and these. So when I run it here, we're going to start on the right motor and work on the proportion and sweep the proportional coefficient between these two values, and you can see the output here. And this is actually, we just captured that off of this motor input. This motor just now. So here we're actually plotting our error. So in the first half a second of the test, everything's neutral, everything's fine. Then we send it an input and say, okay, move 300 encoder counts. So it registers this as an error. And we can see for different proportional coefficients, they're kind of, you'll call them like KP for proportion, KD for derivative, and so on. We can see how they perform. And this coefficient is really just relating, encoder counts to motor speed, or in this case, it's the PWM pulse width that we're using to drive the motor. So it's a very arbitrary kind of scalar. Anyway, so we can see some, have in this case, large overshoot and then a slow oscillation afterwards, and some are quite strong and are actually unstable over time. But this is great to be able to sweep through and kind of programmatically select the best values for this. So likewise, we can look at our sweep derivative terms once we've maybe settled on a proportional term we like. I'm going to run that now. And you can actually see the right wheel here turning every so often, every 2 seconds or so. And this will be good for when E is in the office and you want to do a tuning quickly, so that way I don't have to spend all day kind of tweaking parameters and updating firmware and so on. It should be a very efficient way to do it. Sorry, I'm trying to be fast. It's a lot to cover, and I'm too deep in, but just trying to show a little bit what's going on. So again, we've done the same thing, sweeping derivative values. And so you can see that this is helping our error terms slow down as we approach the correct error. And so, a smaller term is going to get to the correct error faster, the correct value faster, but then, overshoot. So it's about trying to pick a value that, approaches quick enough, but also doesn't overshoot too much. And I think I've chosen something close to this green one. Anyway, so and again, like I've started at much smaller values to kind of scope it in, but this is great for just examining the fine tuning. So then once we have like a control algorithm we think is good, I've done the same thing so that we can sweep different inputs or set points. So if we want to see how the controller performs on a small change in position versus a large one. So again, here we're sweeping the right motor from a 10 encoder count move to a 300 encoder count move. I think like a little over 600 is the full turn. And then these are our proportional and derivative terms. And so here is the response. These are different, we're plotting different set points. And you can see they're different sizes based off how much of an error it generates when the new set point arrives. So here's a very small one. This actually maybe isn't so good because given how small the input is, it kind of overshoots by quite a bit. But you can see that they're all kind of closing out at about the fastest rate they can, given the mechanics. So this actually looks like a pretty good solution. And I think we're pretty much ready at this point to put the robot on the floor and make sure that there's nothing crazy happening that I can't perceive through the screen. Hopefully no weird motor ticks or anything like that. I don't think it'll be a problem, but I think this method's going to help us get a solution very quickly. I mean, I think this is almost good to go. I just expect that it's going to be a little slow once it's under load. Anyway, I hope you guys are all feeling well and this video made an amount of sense. I've been working on this all day, so hopefully I'm not 5 levels too. anyway. Yeah, we'll try to set up a time with EE this week to actually finish this off. Anyway, best regards, guys.